Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. So if you're watching this video, you should have already watched a video on the chain rule, concept, theorem, and proof. The proof is pretty gnarly, but the concept, very important for us in calculus. The chain rule is going to occur almost every single problem that you have from this point forward. So you got to really have a strong grasp of it. And that's what my examples are designed to do. So let's go ahead and jump into some. All right, we're asked to differentiate this function, y equals secant of x squared plus x. So the outer function is the secant, and the interior function is the x squared plus x, which I meant to put in a different highlighter, but it just didn't happen to work. There we go. So what I'm going to do is label the interior function and go ahead and work from there. I'll let u equal x squared plus x, and that means that y is equal to the secant of u. Much easier to tackle both of those. And so if somebody says I need the derivative of y with respect to x, I could start by saying, well, you know what? As I've written it, y is not a function of x. Y is a function of u. And then I can hop inside of y and take the derivative of u with respect to x. So this actually works beautifully. The derivative of this y with respect to u is secant of u tangent of u times the derivative of this u with respect to x. Remember, use parentheses here. It's very important that you take care and use parentheses. So the derivative of that u is going to be 2x plus 1. Now this is actually not the derivative of y with respect to x because we haven't cleaned it up. You still have these u's in there, though our function was not really a function of u, so we're going to have to trade those out. Luckily, we know what u is equal to, x squared plus x. So this will be the secant of x squared plus x times the tangent of x squared plus x, and then finally times 2x plus 1. Again, these are like links. This multiplication is a link, like within a long chain. So you can think of a chain. It's just a bunch of links connected together. Each one is the derivative of the interior function. So you have this outer function you took the derivative of, and then you attach to it the derivative of the inner function, and you attach to that the derivative of the inner function of that, and so on and so forth down the line. So each time I do a problem here, I'm going to do it in Leibniz notation, and then we'll go back through and do all the same problems again, but using Lagrange's notation. It's not that one is better than the other, although I will say Lagrange notation in a natural understanding of the derivative of the chain rule process using derivatives is better. It's still, Leibniz notation is incredibly important. So I'm going to stick with that for a little bit. Then we'll rewind the tape and go back through these examples very quickly using Lagrange notation. In the meantime, we continue forward. So here we have a function f. It's something raised to the third, and the something is a quotient rule. So I could technically write this as maybe a nesting of, well, actually, no, I couldn't technically. It's only the nesting of something within a cubic. That's it. The something is a quotient. So I'll let y equal u cubed, where u is equal to e to the x over x squared plus 1. Notice there's no other compositions going on, so that's pretty good. The derivative of y with respect to x, or somebody will say df dx as well, by the way, that's perfectly fine, is going to be, well, the way I've written it, y is a function of u. and u is a function of x. Now I like this problem because it involves previous material, so they get more complex as you move forward. The derivative of that y with respect to u is 3u squared times the derivative of this u with respect to x is a quotient rule. The derivative of the numerator is e to the x times the denominator, which is x squared plus 1, minus the numerator times the derivative of the denominator, which is 2x, all over that denominator squared. Now you can see that these start getting more robust as you move forward. It's critically important that you pay attention to that. We are not done with this because we have a mixture of variables. You have to resubstitute in what u is equal to. U is equal to that e to the x over x squared plus 1. It is super helpful to factor in the end as well. So I'm going to start with 3e to the x squared, which is e to the 2x, over x squared plus 1 squared times, and then in this group right here, I was actually just using my pen to circle above it, but obviously that's not going to help you. I'm going to factor out an e to the x, and I'm left with an x squared minus 2x plus 1, which factors actually, all over x squared plus 1 and quantity squared. And factoring further, we get that to be 3. These two e to the x's upstairs are multiplying, so that's e to the 3x. And like I said, this factors to x minus 1 quantity squared, all over x squared plus 1 and quantity to the 4th. And that's actually as good as it gets. Doesn't get any better than that. So, but you are expected to simplify as much as possible unless otherwise stated. So often you can get into some gnarly situations where I would normally tell my students, you know what, just take the derivative, but don't simplify. But this is a case where I'd say, take the derivative, simplify your answer as much as possible. All right, again, I'll go back through these in a different ink using Lagrange notation. All right, let's differentiate this guy. Now, I should mention here, this is actually what I would call a double nest. It's a nesting within a nesting. Now, these styles of problems are actually fairly challenging. I'm going to mention to do this the other way. I recommended starting with the innermost function here, but honestly, I think in this case it would be better to work with the outermost. We're going to let y equal u to the 1/3. Okay. And remember, we want to take the derivative. Let me write this down here. We want dy dx. But right now, we're taking the derivative of y with respect to u, right? And then the derivative of u with respect to x, if we say, therefore, u is equal to x plus the cotangent of x squared. So far, I think that's okay. When we do that, the derivative of y with respect to u is 1/3 u to the negative 2/3. All right, times the derivative of this u, and here's where it gets tricky, the derivative of that function u with respect to x. So notice there's a summation there. I'll just group it and say there's a summation going on. The derivative of x is 1, but the derivative of this cotangent of x, derivative of the cotangent of x being squared, over x, that's a problem. So we're going to have to focus in on that here. I'm going to go ahead and clean this up. I'll call this 1/3. The u was equal to the quantity x plus cotangent of x squared and quantity to the negative 2/3 power. And then we're multiplying that by 1 plus. Now I need the derivative of the cotangent of x squared. So I'm going to go ahead off to the side here and say, well, we'll go ahead and let v equal the cotangent of, well, let's call it something else. W maybe, right? Where w is x squared, right? And so the derivative of v with respect to x is really what we're asking to compute here. However, the derivative of v with respect to x, let me finish writing all this stuff out, negative 2/3, is the same thing as the derivative of v with respect to w times the derivative of w with respect to x. Now here's where Leibniz notation really can fall apart. And so that's why I'm not always using Leibniz notation when I do the chain rule. The derivative of v with respect to w, well, the derivative of the cotangent is the negative cosecant squared, so I'm going to write minus cosecant squared of w. And then times the derivative of w with respect to x, that's just times 2x. And now finally, I'll go ahead and replace that w. And you can see that this is just, it's a lot to go through. And I think you can, by the way, you can rewrite the order on that. That's what I'm kind of doing while I talk. So I think that this is a good point to now reveal, kind of like the wizard behind the curtain. Let's reveal a faster method to do this, because I think a lot of people will struggle with just using the Leibniz notation constantly, because it does become an issue as time goes on. So we'll start back here. Differentiate the secant of x squared plus x. Now, Leibniz notation we have already used. Let's use Lagrange notation. And Lagrange notation says this: if you want to take the derivative with respect to x of f composed with g of x, you would just take the derivative of the outermost function, evaluated the inner function, times the derivative of the inner function. So you're peeling away layers. Let me showcase what I mean by that. So all my Lagrange notation will be done in blue. We are given that y is equal to secant of x squared plus x. So y prime will equal, derivative of the secant is the secant tangent. And in fact, let me use a different ink for the interior. I'll use just red for now, x squared plus x. So I have taken the derivative of this outermost function. It's gone. Remember, you have to still insert the argument inside here, by the way. Now to that derivative, I will attach via a chain, a link, if you will, the derivative of the inner function. And the derivative of the inner function is 2x plus 1. Notice how fast that was. Secant of x squared plus x, and notice also that it matches, times tangent of x squared plus x times 2x plus 1. Let's do it again. Here is that problem. F of x is equal to the cube of e to the x over x squared plus 1. Well, again, all I'm going to do is write f prime of x. Actually, let me write f of x here. So f of x is equal to the outer function, I'll write in blue. The inner function, I'll write in red, just to really showcase this. This is e to the x over x squared plus 1. All right, so the derivative of f is the derivative of the outer function, 3 times something squared. Of course, when you take the derivative of the outer function, you have to rewrite the inner function, so e to the x over x squared plus 1. Now, on the outside of that outer function, I will attach via a link the derivative of the interior function. The interior function's derivative is e to the x times x squared plus 1 minus e to the x times 2x all over x squared plus 1 squared. And that at least quickly gets us down to this point right here. It's very fast. Of course, you would clean that up to make it become this, but we've already done that algebra. So you could see that this ends up being a lot faster when you view the world through Lagrange notation rather than the Leibniz notation. Even though Leibniz notation is really good, strong, motivating notation for the chain rule, the reality is you're really just peeling away layers. When I took that first derivative of the outer derivative of something cubed, I should have erased that and just said, okay, now what do we have left to take the derivative of? Oh, e to the x times x over x squared plus 1. Let's do that, attach that with a link. All right, let's try the next one, the harder one. So this was the example where we kind of turned the corner and we said, okay, well, Let's go ahead and go back through and do all those problems with Lagrange notation. And that was just probably less than a minute ago that we did that. So now that we're here, how would you do this using Lagrange notation? Look at all the work we did for Leibniz notation. Well, let's see. I'm going to rewrite the functions always. That's what I always do, is rewrite the function. So I'm going to write it over here as y equals. I'll just use black as the outer layer. So something to the 1/3 power. And then blue for the inner, x plus cotangent. And then I notice there's actually an inside of this function, x squared. All right. So let's start taking derivatives. Y prime is equal to, the derivative of that black layer is 1/3 times something raised to the negative 2/3 power. Subtract 1 from the power, it becomes negative 2/3. And of course, you have to repeat what's on the inside, so I'll just write x plus cotangent of that x squared. Okay, and then I can say, well, because this is why I write this, now I can erase the outer layer and say, okay, what's the derivative of that? I'll attach that via a link. And I don't have room. Let me see if I can quickly make some room here. There we go. Just shove that over to the side. So here we go. I'm going to go ahead and attach with a link the derivative of that blue layer. Remember, that is, you're going to do that with a parenthesis. If you don't use parentheses, you're incredibly wrong. The derivative of x is 1. Sweet. That one's done. And then the derivative of the cotangent is a negative cosecant squared. So I'm done with all that. Of course, inside that cosecant squared is a nested x squared. It was, now let me repeat that. Inside the cotangent was the nested x squared. And so when you take the derivative of that nested x squared, you're going to attach it to the derivative of the cotangent, not outside. Your nests always are attached to what they're nested within. This x squared was within the cotangent, so its derivative will be attached to the derivative of the cotangent. So let's take the derivative of that x squared, it's 2x. And notice I did in one line what took us that many lines before. It's a very powerful technique. So you can see why I hold off on teaching the Lagrange method. It's mainly because if I teach that first, nobody will listen to my Leibniz conversation. They'll just tune out. I like the other one better. But if you've paid attention this long, then you're gifted with the fast method. So let's use that fast method here. This is a beautiful example. I'm going to rewrite the function so that I can erase things. H of x is equal to some big grouping symbol of sine, of a big grouping symbol of cosine, of a big grouping symbol of x squared plus 4x. I should color code, darn it. So it's a big grouping symbol of a red sine, of a green cosine, of a blue x squared plus 4x plus 5, and that ends the green group, that ends the red group, that ends the black group to the 33rd power. All right, let's take the derivative. Just like you would peel an onion, outermost layer first. What is the derivative of something to the 33rd? You're right, if you said it. 33 times that something to the 32nd. Well, what was the something? You could just rewrite that. I'm going to use just black ink to rewrite that. Sine of cosine of x squared plus 4x plus 5. Now, to this derivative, I will attach the derivatives of what's inside. So here I go. I'm attaching to that. And I don't know if I could fit it all on this page, but I'll try my best. I now attach the derivative of the sine. So I've taken care of the outer layer here. Now I've peeled that away. What's the derivative of the sine? Why, you're correct. It's the cosine. Cosine of something. The something is the stuff inside, which was a cosine of x squared plus 4x plus 5. So I now have taken the derivative of the sine. And then you ask yourself, great, I'll attach to that, or no, you don't ask, you tell. Tell yourself, great, I'm going to attach to that the derivative of its interior, which is the cosine. What's the derivative of the cosine? Why, you're right, it's a negative sign. However, just be very careful. Don't write it like this because it looks like a subtraction. Move that negative all the way out to the front here. It's just better for you to do that. Let me make myself some room. Scoot that over. I'll write the negative all the way out front. So a negative sign of whatever's inside that sign, which is x squared plus 4x plus 5. And I didn't leave myself a ton of room, so I'll just rope this up and scoot it over so that I have enough room now. And to that, now that I've taken the derivative of the cosine, let me zoom in. I want blue. I'll delete my cosine. I've taken that derivative. Now I'll attach to that derivative the derivative of its interior, which is the derivative of that blue ink, which is a quantity 2x plus 4. I would not ask you to simplify that because there's just no way you can. But that is the full derivative of h. The chain rule is a beautiful rule. Notice how complex that function is. And you can take the derivative of it. That's pretty amazing. And I can make these up all day. So generally when it comes to my exams, I have something of this size. So you have to be kind of careful. You have to be very good at following the nested derivatives. As a final example, let's see what's wrong with the following computation. I'm just going to showcase what a student has done before. They see that sign, they say, "Whoa, it's a derivative of sine of something on the inside." So the derivative of the sine, this is what the student does. The derivative of the sine is cosine, great, of the stuff inside. Let me get that clean. Of the stuff inside. So that's x to the 5th plus 4x squared. And they say, great, what's the derivative of that? Oh, that's 5x to the 4th plus 8x. Great, what's the derivative of that? Well, that's 20x to the 3rd plus 8. Great, what's the derivative of that? Oh, that's 60x. Great, what's the derivative of that? Oh, that's 60. Awesome, I'm super happy. Whoops, that's 60x squared actually. So this is going to be 120x. Sorry about that. And they say, great, now what's the derivative of this? That's 120. And they say, great, what's the derivative of this? That's 0. And so this derivative is equal to 0. If you argue that way, all your derivatives are going to be 0. So what did that student do incorrectly? And by the way, this has happened not just once, but many times in my career where students get derivatives equaling 0 all the time. Here is the issue, and here's how you can avoid it. The student is not looking here for their nests. They keep looking at their previous work for the nest. If the student were to do this correctly, they would say, okay, I need the derivative of an outer function, sine, of an inner function, x to the 5th plus 4x squared. And so if they do this correctly, they'll look at this function and say, okay, the derivative of the sine is definitely the cosine of the inner function. Great. That is perfect so far. And then, if they so choose, they'd probably erase that. And then they'd look at this inner part and they'd say, okay, what's the derivative of that? I'll attach that with a chain. That's 5x to the 4th plus 8x. And notice there's nothing else to take derivatives of. So you save yourself a little bit by rewriting the function and then erasing as you move forward. What this person did is they took the derivative of the outer function, sine, and rewrote that. And then instead of looking at what they were working on, they looked here, took the derivative of that. They wrote it here, but then they took the derivative of this. And they wrote it here and took the derivative of this, and so on and so forth. So that's what's wrong with that computation. Just be very, very careful when working using the chain rule. There are so many pitfalls or traps that you can fall into with the chain rule. And it is probably, of all the derivative rules, the most important in my opinion.
It's the system of equations we must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.